autoionization of water. So I mentioned that water is amphoteric, meaning it can act as either an acid or a base. Autoionization, kind of like an autoimmune problem, autoionization is the process whereby water forms ions all by itself. It makes acid and base by itself. So how does that work? Well, here we have water acting as an acid. Here's the base. The base can donate a hydrogen ion to the water, the acid donates a proton to the ammonia, and we get hydroxide. Down here we have water acting as a base, where it's accepting the hydrogen ion. What happens only to a small extent is that two water molecules can get together and one can donate a hydrogen ion to the other one. Now, why would they do that, right? Most things are going to be the same, right? If you have two water molecules and they're the same, you'd think, well, they're just going to stay the same, right? But here we have one, for who knows why, deciding, well, I'm going to donate my proton to you, so that makes me the acid and you're the base, and now that we've done that, I'm the base and you're the acid. Not confusing at all. So this is the autoionization of water, water ionizing itself, forming a cation and an anion. This water molecule acting as an acid, that one acting as a base. Notice the equilibrium arrow there. If we write it just looking at H plus instead of the hydronium ion, then it looks like a water molecule coming apart to hydrogen ions and hydroxide ions. So we can write an equilibrium constant expression for these equilibria. This is Kw. It would be hydronium ion concentration times hydroxide ion concentration. Or if we're ignoring that extra water molecule, H plus times OH minus. So Kw, this is called the ion product constant for water. That W there is for water. So at 25 degrees room temperature, Kw is 1 times 10 to the minus 14. Big number, small number? Small number. That's pretty small. So does this autoionization happen very much? No, it doesn't. Just a little bit. In pure water, when one hydrogen ion is made, you have to make one hydroxide ion, right? Because it came from pulling the thing apart, you get one of each, an equal number. So we can say that the hydronium ion concentration must be equal to the hydroxide ion concentration, and then those would be the square root. They both be equal to the square root of Kw, which is 1 times 10 to the minus 7. So 1 times 10 to the minus 7 is the concentration of hydroxide ions and hydronium ions in pure water. That is very, very small. Here we had water acting as an acid and a base, but pure water is neutral because we have equal concentrations of hydrogen ions and hydronium ions. Hydroxide ions. Any questions? So water is a neutral substance. An acidic solution is one that has extra acid in it. So it has additional hydronium ions. The ion product constant for water still applies. So what happens here when you add in the extra hydronium ions, the autoionization of water, that is shifted to reach equilibrium again, is shifted to the left. So the concentration of hydroxide ions will decrease. and then we'll see that the concentration of hydronium ions is greater than that of hydroxide ions. In a basic solution, a base has been added, so we've got additional hydroxide ions. Let's draw this guy out again. So, if we add hydroxide ions, well, Chatelier's principle here, right? If we add this product, what does that do to the reaction? It's going to shift to the left, and that will decrease the hydrogen ion concentration. So now the hydroxide ion concentration is larger than the hydrogen ion concentration, and that's called a basic solution. So here we have the hydronium ion concentrations of 3 different solutions at room temperature, and we are asked to identify which solution is acidic. So an acidic solution, what's the relationship between H3O plus and OH minus? Which one's bigger? The H3O plus. Acidic, acid, H3O plus, there's more of it, right? But this isn't giving us comparisons, it's just giving us concentrations. Well, what's this guy, right? This is the concentration of hydronium ion in pure water. So this is going to be a neutral solution. So if we want an acidic solution, we want one that has more hydronium ion. The concentration is larger than 10 to the minus 7. Is that A or B? That's A. So this one has more hydrogen ion concentration. Calculate the hydronium ion concentration at 25 degrees Celsius for each solution and determine if the solution is acidic, basic, or neutral. Here we're given hydroxide ion concentrations. So we're going to use the autoionization of water, that ion product constant for water. So Kw, which is 1 times 10 to the minus 14, is equal to the hydronium ion concentration times the hydroxide ion concentration. In an equilibrium, when we put the concentrations into that expression, this is a constant. So if this one goes up, that one goes down, and vice versa, their product is always the same, 10 to the minus 14. So we can find the hydronium ion concentration by taking Kw and dividing it by the hydroxide ion concentration. So there's Kw, 14, divided by the hydroxide ion concentration. And make sure you're using scientific notation correctly on your calculator. So this is going to give me a concentration of 1 times 10 to the minus. No, that's not right. I forgot the 0.5. Wait a minute, how do you do that? There we go. 6.7 times 10 to the minus 13. So calculate the hydronium ion concentration. So there's the hydronium ion concentration. Is this solution acidic, basic, or neutral? It's basic because this one is larger. So this one's basic. Do we really need to do a calculation for this one? No, because if the hydroxide ion concentration is 10 to the minus 7, then the hydronium ion concentration is also 10 to the minus 7. Because that's the product that gives us 10 to the minus 14. Acidic, basic, or neutral? Neutral. And then this guy down here, letter C, the hydronium ion concentration would be Kw, 1 times 10 to the minus 14, divided by 8.2 times 10 to the minus 10. We could actually identify whether it's acidic or basic just by looking at that concentration, but we have to calculate this anyway. .2 times 7 minus 5. Acidic, basic, or neutral? Acidic. Any questions? So dealing with those concentrations that are all times 10 to the negative 13, negative 7, negative 2, just kind of all over the place, is a pain. And so the pH scale is a way to make that more compact. Because really what we're dealing with is orders of magnitude. So the pH scale uses a logarithm to, make it more compact. So the pH of a solution is equal to negative base 10 log, and this is not the anti-log. This is just negative 1 times the base 10 log of the hydronium ion concentration. So if we have a solution that has a hydronium ion concentration of 5.3 times 10 to the minus 8 molar, it has a pH of, we calculate it using this equation. pH is equal to minus 1 times the log of 5.3 times 10 to the minus 8. So that would be 7.28. pH doesn't have a unit. When you're dealing with logarithms, and this is somewhere we should try to keep this straight, with pHs, because this is the logarithm of something, the significant figures are the ones to the right of the decimal point. The 7 is really that place-holding exponent. So if I were to find the pH of, say, a solution that was 5.3 times 10 to the minus 3, well, that's going to be 2.28. Check it. Did it in my head. I'll do another one. Negative log 5.3 times 10 to the minus 14. 13.28. What? So we're taking the base 10 log of this. The logarithm says, what exponent should I put on 10 to get this number? Okay? So here, because these are negative, the 8 is going to become a 7, 3 becomes a 2, the 14 becomes a 13. These digits to the left of the decimal point just come from this 10 to the power. These are not significant figures, they're place-holding zeros, right? The 2.8 part is coming from the sig figs, 5.3. Any questions? So on the pH scale, a pH of 7.0 is what you have for pure water. The hydronium ion concentration would be 10 to the minus 7. So this is going to be neutral. If we go to lower pHs, that means the hydronium ion concentration is larger. And going to higher, higher pHs means the hydronium ion concentration is smaller. And there's that unfortunate bigger, smaller thing there because we were dealing with negative exponents. We can also look at pOH. pOH is just the negative log of the hydroxide ion concentration. Concentrated acid solutions can have negative pH values. It's possible to have negative pHs. Let's see what would happen. If I have a pH that's minus 1, let's say minus 1.0, that was equal to the negative log of the hydronium ion concentration. So I can get rid of those negative signs. And so I'm going to take the base 10 log of both sides. 10 to the 1 is equal to the hydronium ion concentration. So that would be a 10 molar solution. That's pretty concentrated. There are some that are higher, even like 18 molar.
What happens if you touched it with your bare hands?
You'd get it burned pretty quickly.
How bad would it burn?
Well, it depends on how much and how long it touched you. So we can calculate pH from the hydronium ion concentration or the hydroxide ion concentration. I'm looking for... the circle. Oh, there it is. Circle of pH. I knew it was coming up there somewhere. I wasn't sure if I was supposed to draw it here or not. Okay. Calculate. No, we did that one. No, we didn't. No, we didn't. Okay. I'm not confused. Not at all. Calculate the pH of each solution. So here we're given the hydronium ion concentration. So we use the pH equation. pH is the negative log of the hydronium ion concentration. And so that's going to be the negative log of 9.5 times 10 to the minus 9. This is going to be 8 something. This has 2 sig figs, so I'm going to put 2 decimal places. This pH would be 8.02. Acidic or basic? Basic. Larger pHs are basic. This one's basic. You can also identify that looking at the hydronium ion concentration, which is lower than in pure water. Here we're given the hydroxide ion concentration. But we want to find the pH. Well, we could find the hydronium ion concentration and then use that to calculate the hydroxide ion concentration. I'm sorry. We can use this to calculate the hydronium ion concentration and then calculate the pH. So Kw is going to be the hydronium times the hydroxide. So the hydronium ion concentration, which is what we need for pH, is going to be Kw 1.0 times 10 to the minus 14 divided by the hydroxide ion concentration given. One point 408 times 10 to the minus 12. It's a good idea. If you're not finished with the calculation, carry some extra digits. So now I can find the pH. pH is the negative log of 1.408 times 10 to the minus 12. .85. Acidic, basic, or neutral? That's basic. Tricky, they were two of them, both basic. Questions? Okay, going the other direction. Calculate the hydronium ion concentration for a solution with a pH of 8.37. Well, we have this equation. The pH is equal to the negative log of the hydronium ion concentration. We want to find the hydronium ion concentration, so we need to rearrange this equation. So first I'm going to multiply each side by -1. And now it's very tempting to divide by log, but log is not something you can divide by. It is a function. So you're going to do the anti-log, which is 10 to the x. So take the anti-log, both sides, and you get 10 to the negative pH is equal to the hydronium ion concentration. So then we can say, well, then that's equal to 10 to the negative 8.37. But we shouldn't leave it like that. So I'm going to use my 10 to the x, 10 to the minus 8.37. And my calculator is showing me, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 2, 3. But how many significant figures should this number have? 2. What's the next digit?
0.
No, it isn't. My calculator rounded it because it could show it to me in decimal notation just barely. So I can either trick it, multiply that by 1,000 or something to push the numbers over, or I can tell my calculator to show me that in scientific notation instead. And it's actually 25, this. It's this. So we would say that's 4.3 times 10 to the minus 9th molar.
Mrs. K,
Yes?
when you did 10 to the negative 8.37, why is it negative?
Because the pH was the negative log of this. So I multiplied both sides by -1, and that makes my pH negative, but my log is positive.
Okay. Oh, because that's, okay. Thank you.
Yeah. These concentrations are going to be small, generally less than 1, and so almost always the exponents are going to be less than 1. So they're negative. Any questions? So the pOH scale is just defined with respect to the hydroxide ion concentration instead. So here's the pH scale. The pOH scale is exactly opposite. So this mathematical operator, P stands for negative log of. So we can have a pKa. That's the negative log of the Ka. We can put anything in there, x. Px is the negative log of x. You could have the P calcium, the negative log of the calcium ion concentration. Derive the relationship between pH and pOH. Well, we know that Kw is equal to the hydronium ion concentration times the hydroxide ion concentration. So if I take the log of both sides, I'm going to get the log of Kw is equal to the log of H3O plus the log of OH minus. Because the log of x times y is equal to the log of x plus the log of y. So these kind of look like the equations for pH and pOH, right? Except they don't have a negative sign. So let's multiply by -1. Then I've got the negative log of Kw is equal to the negative log of the hydronium ion concentration plus the negative log of the hydroxide ion concentration. What does this represent? pH. And what does this represent? pOH. So I've got pH plus pOH. What's the negative log of 10 to the minus 14? It's 14. The sum of pH and pOH is 14. I'm not going to make you derive that, but I want you to see that we're not making these things up. The circle of pH. So there's 4 things that we can calculate. There's pH, there's pOH, there's hydronium ion concentration, there's hydroxide ion concentration. And they are related to each other in the circle of pH. Oops. So it doesn't really matter what you put on top. So pH is related to hydronium ion concentration. So I can convert back and forth between pH and pH and hydronium ion concentration. Because we know that pH is equal to the negative log of the hydronium ion concentration. And if we want to go the other way, the hydronium ion concentration is equal to 10 to the negative pH. Same color? I think it is. Well, we just learned that pH and pOH are related to each other, rather simply, in fact. pH plus pOH equals 14. So it's pretty easy to go back and forth between those two. The other piece here is hydroxide ion concentration. We can calculate pOH from the hydroxide ion concentration. Oops. Habit. Or conversely, the hydroxide ion concentration is equal to 10 to the negative pOH. Can we convert between hydronium and hydroxide ion concentrations? Yeah, that was like one of the first things we learned. The Kw is equal to the hydronium ion concentration times the hydroxide ion concentration. And that is the circle of pH. So sometimes you need to go from pH to hydroxide ion concentration. You can't just jump across the middle. Could you derive an equation for that? Of course you could. But it's not worth doing. Just go this way or go that way. Which way should you go? Whichever way seems easier to you. I prefer the pOH plus pH thing equals 14 to messing around with that guy. So I'll avoid this guy if I can. But, if I want to go from hydronium ion concentration to pOH, pick one way or the other. Any questions? You should be able to do all of those conversions, all those calculations. As the pH of the solution increases, meaning gets higher, what happens to the acidity of the solution? It decreases. High pH is low acid. And, there could very well be questions along those lines on an exam. And the best thing to do is just to actually talk to yourself in your head. Right? Don't just jump at numbers.